This is section 13.3, and this is the fundamental theorem for line integrals. This is just the introduction to it. We're going to talk about conservative vector fields and the fundamental theorem for line integrals, and then in the next video we'll do some of the examples. So as a quick review, the line integral over C of the vector field f dotted with dr, this equation is calculating the work done across a vector field. And remember, we have a couple other formulas that are really common. This one is the one that we use most often. It's the vector field f of r of t dotted with the derivative vector of r dt. So we use that most often because it's differentiating with respect to t. But then we also have the one with respect to arc length, which is going to be utilizing that unit tangent vector. But again, that's just work done. So if you're doing the work done across a vector field, any one of those would be asking for that. And then a quick review of the gradient. So the gradient vector, and this is bold, but it's really hard to see. So there's a little vector symbol above the triangle there, and we're looking at the gradient as just the partial derivative of a function with respect to x, vector I plus the partial derivative of f with respect to y, and then unit vector j. And then this is just from the last couple of years of calculus, the fundamental theorem of calculus. So if we're looking at this gradient vector, the fundamental theorem for line integrals is directly connected to both of these items that we talked about, the gradient and the fundamental theorem of calculus. Your fundamental theorem for line integrals is simply a line integral of a gradient equal to f of r of b minus f of r of a. So here's what this is talking about. So if you have some sort of line integral, and you start at, let's say, a, and it goes to b. Okay, when you're looking at this particular path and you're calculating your line integral, if the vector field is a gradient field, and that is a big if. So if the vector field is the gradient of some function, so it's produced by the gradient of some function, then what you're going to do is you're going to access A by, think of if this is your x, y, and z planes in space. So then let's say you access A through your vector equation R. So you have R of A, and then you have R of B. Okay, so what this theorem says is that if you have a gradient vector field, then you could calculate the line integral by taking the antiderivative of this, which I'll talk about in a second, which is f of where you end up, so r of b, minus where you started, r of a. Okay, now this function f that they're referencing right here, so this function f, that is called the potential function. And that function, for all intents and purposes, is the antiderivative of the gradient vector. So in other words, if you're looking at this gradient vector, if you were to do the antiderivative, so we're going to talk basically about partial antiderivatives, you're going to get the potential function. You're going to get where it sort of began, okay? And so we'll talk about that in a second. Okay, let's move on, and then we'll come back to all this stuff. Conservative vector field, it's also called a path-independent vector field. This is a vector field f whose line integral over any curve C depends only on the endpoints of C. The integral is independent of the path that C takes from one point to the other. We sort of talked about this a little bit. We did a problem in section 13.2 where we went from one point to another point, and we took two different paths, and we got two different answers. That type of vector, or that field that we analyzed in that example, is not conservative because the path mattered. If you have, let's say, point A and you have a point B, what this is saying is pretty remarkable. It's saying that if you take this path right here, call it C1, to get from A to B, and you did this path here, call it C2, from A to B, the line integral is identical in value if this is a conservative vector field. If it's not a conservative vector field, then often those values are very different. But if it's conservative, if your line integral for C1 is 7, the line integral for C2 would also be 7. How do we test whether a field is conservative? Well, basically, this is a relatively simple test. But basically, we're going to say that we're going to sort of assume that f is conservative. So let's say that we assume this. So if the vector f is conservative, and it says this in the theorem, but I'm just going to write it right here. So we're letting this vector f be the vector p, q. Okay, we're just giving it two different variables there. So if f is conservative, then this vector f is equal to the gradient of some other vector, something f, okay, little f. All right. If that's the case, then vector f, which is pq, would be the same thing as writing the gradient little f equal to the partial of f with respect to x and the partial of f with respect to y. And that's basically, this is just the definition of a gradient vector, and that's in your notes just above where we are right now. Okay. Now, again, if this capital F vector field is conservative, then it is equal to a gradient vector by definition of what we're kind of classifying as a conservative field. What that means then is that the component P is equal to the partial of f with respect to x, and similarly the component q is equal to the partial of f with respect to y. Okay, so all this is saying is that if you have a vector f which is made up of p and q, and you're going to say that it is conservative, then these two components, p and q, are equal to the components of a gradient, which is going to be the partial of f with respect to x, partial of f with respect to y. Okay, now if we were to take the derivative of the second derivative, excuse me, of f, so I'm looking at this first one here. Okay, we know that that if we took the second derivative with respect to y, it is equal to the second derivative of y with respect to x. So in other words, we know that by Clairaut's theorem that the second derivative, depending on the order, does not matter to us. So the second derivative of f with respect to x and then y is equal to the second derivative of f with respect to y and then x. We know that for sure. If we think about this, the one that we've written over here on the left side, this is the equivalent of the derivative of p with respect to y. Because if p is equal to f of x, the derivative of f with respect to x, then the second derivative written with respect to x first and then y is going to be the derivative of p with respect to y. And over on the right side, if we were to take q, so this is q right here, and take the second derivative, again with respect to x, then we will get the second derivative of f with respect to y first and then x, and we get the derivative of q with respect to x. And if you notice, what we've done is we've just written this equation out, and this equation is a really quick test for whether or not a certain field is conservative. So if we're trying to answer the question, is a certain field conservative, we're going to test it using this technique. And again, the technique is essentially take the first component and differentiate with respect to y, take the second component, differentiate with respect to x, and see if they're equal. And if they're equal, it's conservative. If they're not equal, then it's not conservative. If it is not conservative, then again, going back up here to our little picture, if it's not conservative, then the path probably matters from one point to the other, most likely. If it is conservative, then the path won't matter at all. Okay, the next video will be on our first few examples.